Welcome, everyone, and thanks for joining us for this session on data engineering for ML and AI with AWS Analytics. So in this session, we'll be talking about how you can build a data strategy for your AI ML applications and how you can use AWS Analytics services to build that data strategy. My name is Uday Narayanan, and I'm a Principal Solutions Architect at AWS, and I'm joined today by Tim Kraska, who is a Director of Applied Sciences at AWS, and also a professor at MIT, and Mo Haider, who is an engineering leader at Nexthink. So let's look at our agenda, right? So today we'll talk about the importance of having a data strategy for your AI ML success and how you can build that data strategy using AWS Analytics services. Then we'll have Tim, who's going to talk about patterns for converting natural language to SQL and how to use structured data as part of your GenAI applications. He's also going to talk about a new feature that was announced earlier today by Swami during his keynote. And there's also a demo, so stay tuned for that, exciting stuff. And we have Mo, who's going to talk about Nexthink's journey of how they built a GenAI-based ticketing system using AWS services. So again, like really cool story there. All right, so this is an AWS session, right? So we have to do one show of hands exercise. Now, it's evening, I understand, so let's do an easy one. How many of you have some AI ML application running in your organization today? All right, I was expecting more, but I'm guessing it's late evening, so it's okay. But in general, right, there's a lot of excitement today for AI and GenAI in particular, because they help you transform customer experiences, improve employee productivity, and just overall improve your business operations. And there's a lot of use cases today for GenAI, for AI and GenAI, from virtual chat assistant, which we'll talk about more in the coming slides. But there's also text summarization and code generation, which can help improve employee productivity. There's also traditional AI ML use cases like retail demand forecasting, predictive analysis, sentiment analysis, and so on. Now, when you're building these applications, there are a few things that you need to do right to make sure that these applications are successful and adopted by your customers. But the most important thing is to make sure high-quality data is available and accessible for your machine learning models to be trained on, right? Because your data is the key differentiator in making sure that your customers have a personalized experience when they are accessing your applications, and that is what makes them adopt that application even more, which makes them successful. Now, in order to make sure that all of your data is available for your applications to be trained on, you need to have a data strategy in place. So let's look at how you can build a data strategy, like what are the building blocks that you need to make sure when you're building these end-to-end pipelines. So in today's world, we have a lot of different data sources, which could be either structured or unstructured. So the first step is to make sure you're bringing in all of this data, or you're ingesting all of this data to bring it to a central location, right? This could be batch ingestion or streaming ingestion. You're ingesting it and bringing it into your enterprise data lake. It's usually recommended to bring it in the raw format so that in case there is a scenario where you want to reprocess the data, that data is available for you. This data is then processed using some ETL tool where you're building some ETL logic, data transformations are put in place. The data is brought into a structure that is easily consumed by your downstream applications. This transformed data is then cataloged, and then data governance rules are put in place, such as data privacy, data access control, to make sure the systems and users who need access to the data have the access, and the users who do not need access to the data, you don't give them access, right? You need to make sure that principles of least privilege are followed. Now, this data is made available to your business units and other users within your organization, and they can build their data processing pipelines, generate training, validation data sets for machine learning, transform the data, load it into a vector data store for any kind of GenAI use cases, do feature engineering, and so on. Now, the training and validation data sets are made available for your AI models, and then the models are trained, applications are built on top of it. There's also a scenario where you might need like a feedback loop, where as users are interacting with your application, there could be valuable information that you can capture from that, which you need to send back to your data lake and can be used for any future tuning or fine-tuning of your models. So this is all well and good, but now you might be thinking, okay, but how is AWS going to help me with this? So let's go through the same flow, but with AWS services. So again, we have these different data sources. To ingest the data, you can use AWS Glue that can connect to over 70 different data sources using Glue connectors and bring that into a central location into your data lake. Now, if you have a streaming use case, you can use Amazon Managed Streaming for Apache Kafka and Kafka connectors to connect to your different data sources. If you want more like AWS native solution, Amazon Kinesis Data Streams is also a good choice. Now, what if you have a scenario where your data is sitting in an on-prem environment? Like we talked about earlier, we want to make sure all of your data, or as much of your data, is made available to your machine learning models to be trained on. So for on-prem scenarios, you can use AWS Data Sync to connect to your on-prem data stores and bring that data into your data lake. Now, in this case, all of this data is ingested into your data lake in Amazon S3 in the raw format, like we talked about earlier. And we can build data processing pipelines or data processing jobs to clean the data, do some validations, data quality checks using either AWS Glue or Amazon EMR. With AWS Glue, you actually get built-in data quality features where you can build data quality as part of your ETL pipelines. Now, this transform data is then cataloged using AWS Glue Data Catalog, and you'll build fine-grained access control on top of it using AWS Lake Formation. It's also recommended to have a business catalog on top of it, which makes it easier for your analysts and non-technical users to easily find the data using business semantics or business meaning or business context. And you can use Amazon Data Zone to build that business layer on top of your technical catalog. Now, once this data is made available for your downstream applications, you can do data processing using AWS Glue, Amazon EMR, or if you are a machine learning scientist who wants to do everything end-to-end using SageMaker, SageMaker Data Wrangler is another option. It's during this process that you will generate the training validation data sets. You can also do vector data management and store data into your vector stores like Amazon Aurora or Amazon OpenSearch for any GenAI-based use cases where you want to use RAG. Now, this training and validation data set is used to train models, which can be either on SageMaker AI or Amazon Bedrock, if it's a GenAI use case. And then you have a GenAI-based application, which is using these models, which your customers are interacting with. Now, as users are interacting, you want to make sure that the session information and the context is maintained as follow-up questions are being asked. So in those cases, you can store the session information and context in Amazon DocumentDB or Amazon DynamoDB and so on. All right, so now let's take a deeper look into some of these services that we talked about and talk about some of the best practices that you might want to follow when you're working with these AWS services. We'll start with streaming and Amazon Kinesis Data Streams. So Amazon Kinesis Data Streams is a serverless solution which can be used to stream gigabytes of data in seconds. And it's a serverless service, right? So you're only paying for what you use. Now, in Amazon Kinesis Data Streams, one recommended best practice is to make sure that you're aggregating and compressing your data before you write the data into your Kinesis streams. Now, to do that, you can use Kinesis Producer Library, which makes it easy and provides built-in capabilities to easily compress and aggregate the data. On the consumer side, you can use Kinesis Consumer Library to easily de-aggregate the data. But at the same time, Kinesis Consumer Library also provides you checkpointing and fault-tolerant capabilities. So if your application goes down, and it's a streaming application, and it comes back up, it kind of knows where to start from or where it left off. Now, Kinesis, your stream is divided up into multiple shards, and each shard has a 2 megabyte per second throughput per consumer. So if you have multiple consumers, the 2 megabytes per second per shard is actually shared by those multiple consumers. So if you have a scenario where you have multiple consumers reading from your Kinesis stream, the recommendation is to use enhanced fan-out consumers, because with enhanced fan-out consumers, each consumer gets dedicated 2 megabytes per second per shard. So you won't run into a scenario where if you're adding more consumers, your existing jobs are suddenly running slow because it's the throughput is being shared, right? Each consumer gets its own 2 megabytes per second throughput. And with Kinesis, you have the option of using on-demand or provision modes. So recommendation, again, is to start with on-demand. Once you understand your traffic patterns, and if you have a predictable pattern, you can go with provision mode. With Amazon Managed Streaming for Apache Kafka, make sure that your CPU utilization for your cluster is at or around 60%. This is to make sure that in case of any operational event or like a broker going down, you have enough headroom for it to recover. Now in MSK, every node, or every node type will have a maximum throughput that it can support. So again, the recommendation is to stay at or around 80% of the maximum CPU that is supported. Build highly available clusters, which pretty much means make sure that when your MSK clusters are being spun up, it's spun up across 3 availability zones with a replication factor of 3, which means all of your data and topics are replicated across 3 availability zones. And minimum in-sync replica of 2, which means if one broker goes down, your cluster just continues to operate as normal without any issues. And then finally, around 3 weeks back, we launched Express Brokers for MSK, which provides high throughput and faster scaling compared to regular brokers. So if you are a current MSK customer or considering using MSK, I would recommend testing out Express Brokers for your use case. Oh, and as we are going through the session, we are sharing some additional reading to deep dive into some of the topics that we are talking about. So you can scan it here, and if not, then we are also providing a summarized slide which has all the links together, so you can take a picture at that time as well. All right, now talking about data integration with AWS Glue. Make sure that you're right-sizing your workers. So with Glue, there are different worker types, and worker type pretty much means the amount of CPU and memory you get per executor. So make sure that you're right-sizing it, and the best way to do that is by going into the Spark UI and just analyzing how the executors are being used and how they're being leveraged for your job. And with Glue, you have one-click access to the Spark UI. Make sure that you're using Flex execution for any non-time sensitive jobs. So Flex is just spare capacity that we have. So when you use Flex, there could be some delay in the job starting, but it gives you cost savings. So because there's some delay in the job starting, the recommendation is to use it for non-time sensitive jobs. If you have incremental processing requirements, make sure that you're using job bookmarks, because with job bookmarks, you can keep track of what data has been processed so far, and when the job runs the next time, it will start from the point where it left off. And then in general, right, for Spark optimization, make sure that you're optimizing your shuffles and you're doing predicate pushdowns to ensure that the amount of data that is being transferred over the network is minimum. With Amazon EMR, make sure that you're, especially this is for EMR on EC2, if you're using make sure that you're using the right instance type for your use case. So if you have a compute-heavy workload, make sure that you're using compute optimized. For memory-heavy, use memory optimized, and so on. Using Graviton instances usually provides you considerable price performance compared to x86. So that is just a way for you to get price performance benefits without having to really go and tune your code. And then use the latest versions of EMR, because as new versions of EMR are being launched, we are bringing incremental performance improvements into the engines that we're running, right? So if we have EMR 6.x versus 7.x, the Spark that is running on 7.x usually has a little bit of better price performance compared to the version that is running on 6.x. All right, so we talked about ingestion and data processing. Now, data quality is a very important factor, because when you're training your machine learning models, you want to make sure that you are training them with high quality data. So with AWS Glue data quality, you can build these data quality rules in different parts of your pipeline. So here you can see we have these different data sources. We are connecting to those different data sources using Glue connectors and cataloging all of that data inside the Glue data catalog. In the Glue data catalog, you can configure these data quality rules and have them run every time a data refresh is happening to make sure that the data quality with the new data still is at the level that you want it to be. But with Glue, you can also do data quality inline, meaning as part of your Glue ETL job, you can have a data quality transformation, which can check for data quality based on the data quality rules that you have provided. And if it meets the data quality rules, the data can be written into your data lake. And if it does not, then it can be written into a separate section. You can review the data, make sure that it's all good, and then write it to your data lake. So there are different ways that you can put in data quality rules. And then finally, with data governance, make sure that any data that you have is cataloged inside your technical data catalog. With Glue Data Catalog, if you have a table with a large number of partitions, you would usually see some performance hit. So make sure that you're using Glue partition indexing and partition filtering to ensure that the performance is up to par as you want it. And then running statistics is very important because Athena and Redshift cost-based optimizers are using the statistics to build this optimal query plan for your queries. So make sure that you're periodically gathering and running stats on your Glue tables. When you're configuring lake formation for fine-grained access control, we want to make sure that you're using tag-based access control because it helps you scale your administration of your lake formation or administration of your fine-grained access control. So basically how the tag-based access control works is you assign a tag to a table. Then in lake formation, you say, like an analyst user can access any table that has this particular tag. Now, as new tables are getting added, you don't have to configure fine-grained access control for each individual table. All you have to do is create a table with that specific tag, and because you've already granted lake formation permissions for that tag, the analyst users can access the new tables. And then finally, just as I talked about earlier, ensure that you have a business catalog in place. It just makes it a lot easier for your non-technical users like analysts or business users to find the data that they need for any kind of analysis they're doing. All right, so now that we have talked about data ingestion, data processing, data quality, and data governance, we are ready to start using the data for our analysis. So in terms of GenAI, there are a few different ways that you can access the data or use the data, right? The easiest way would be to do like prompt engineering, where you're just taking relevant information from the different data stores, generating a prompt, and sending the prompt into your GenAI application to get a response back. You can also do RAG, or Retrieval Augmented Generation. With RAG, you're doing, like you take with a question from the user, it's tokenized. You look up into a vector data store, like an open search data store, to get semantically relevant data back. That is added to your prompt, and then we send it to the GenAI application to get the response back. Now, sometimes contextual prompt engineering and RAG is not enough. So you might want to do some fine-tuning of your data. So fine-tuning of your models. So that would be the third option. And then finally, the most complex and the costly option would be to train your own models, which we haven't seen a lot of customers do. So in this talk, we're going to mainly focus on the RAG and the RAG approach. And then Mo is going to touch on the fine-tuning a little bit as well. So with that, I'm going to hand it over to Tim to talk about how you can use structured data as part of your RAG applications.
Thank you, Uday. So I mainly want to talk about how we can leverage structured data as part of our applications. The little bit of background about me, I'm a director of applied science at Amazon, and I mainly work on the intersection of machine learning and systems. For example, my team did this feature called generative SQL as part of the query editor v2 in Redshift. As Amazon always puts it, so I recently had a meeting with HR, and I always need to justify what I still do with academia, and every year they say like, oh yeah, as a hobby, you can also still be a professor at MIT. So I'm still doing that as well, where I lead like a bunch of PhD researchers to work on generative AI topics as well. So diving directly into, so what is a typical flow on how to create a generative AI application? What I will cover first is on how to do something with documents, meaning that you have documents stored, let's say, on S3, and you want to build a generative AI experience over it. So for that, it's like normally what we refer to as a RAG is a typical state-of-the-art approach, right? And I take like fine-tuning and other things out of the picture for now. So how does it work is an end user issues a request, a user query, which goes to the applications you are trying to build. Then the request is routed to like normally an embedding model, which might be hosted on Amazon Bedrock. The embedding is sent to like a vector store, like OpenSearch. You find the most similar documents using the vector search, and then you take the top K of that and you put it in your prompt. You might, in addition, include some conversation history as part of the prompt, right? And so this becomes essentially a very large text string. That is what it is. And the whole text string is then sent to your model of choice, which might be, again, hosted on Bedrock, and it gives you a response back, which is then sent back to the user, right? So without the Bedrock platform, normally you have to implement all of that by yourself, right? You have like some Python running somewhere, you set up an OpenSearch, you need to host the embedding model and so on. The nice thing is, with the Bedrock platform, this process becomes extremely easy. And in particular, creating a knowledge base, which is our term for building a RAG, is just like can be done with a few clicks, and you just set up and running. Yeah, so you can just like say, okay, which foundation models I want to use. You can set like what types of embeddings. You point it to, let's say, a bucket on S3 with your documents, and you're good to go. Even more than that, there are now like a bunch of out-of-the-box connectors, for example, for web crawlers, like SharePoint and others, where you can just treat these documents in these other third-party systems as just like out of the box without extracting them first, right? So it's very, very easy, right? So this is like the whole process of just building a RAG. But unfortunately, often just like our most important data is not stored in documents. It's like in other systems like databases. Like what we just heard before was just like how to build the whole pipeline to clean your data and prepare it and transform it so that it ends up in a data warehouse, right? And you want to make probably this data, which is like the most valuable, which is already cleaned in a nice format available for your generative AI applications as well. And there are plenty of use cases around what you want to do with them. For example, you might want to build a Slack assistant, which can answer questions around like finance, marketing, offices, like what is my campaign currently costing me? How does it compare to last month? And so on. It would be really nice if like these standard analytics questions could be just, for example, answered as part of a Slack channel, right? Or you might want to build your custom portal assistant, like internal or external, where you can give access in a like very easy way through these like new generative AI assistants to other people. Unfortunately, moving from like these documents and unstructured data to more structured context is not that easy. And the problem is that in contrast to if you have a document, a single document normally doesn't contain your answer, right? Instead, you have a schema where everything is like in a typical case not like it's normalized, meaning it's like over several tables. And in order to answer a question like, what was the revenue last month, you actually need to translate this to a query, which then can provide the answer you want to integrate, right? So the big first insight I want you to take away here is that natural language to SQL, the process of translating a request to SQL to a query, is essentially the equivalent of RAG for structured data, right? It's like the same thing as what you need to do in order to get an embedding, the most similar documents and other things. In the case, if you want to integrate data from a database, you need to figure out on how to query it based on the requests, right? This process in itself is actually quite hard, and there are a lot of challenges with that. So why is it hard? Like the first thing is, if you ask, for example, a question like count the numbers of schools in Alameda County that have fewer than 100 test takers. So this is like a public data set you can get about test takers. It's from gov.org. We just downloaded it. If you ask large language models the question, oh, give me a query for this, it would actually generate something. The problem is it might have nothing to do with your particular schema, right? You might have to do something very, very different in join tables in order to answer it. So in order to generate the right question, you need somehow to teach the model on how to create the query given the context you are in, given your schema and other things, right? So it needs to be personalized to your database, tables, and schema. The other thing is, like, if you have a question like list the product description of transaction and gas station in the Czech Republic, again, this is based on a training data set we normally use. It might give you a query like this, and now here we assume we actually already took the step of teaching it about the schema. So now what you see here is like filtering by country, by republic, but it just happens to be that this is encoded in a complete different way, right? Like with the abbreviation. This is very, very common. Like let's assume you want to see revenue in California. You need to know if revenue in California is encoded as California, CA, as zip codes, or even something completely different, right? The last thing is then that, so you really need to personalize this to your data as well, not just the schema. The last one is like every single database we have has like a little bit of different behavior, different syntax. So there's a SQL dialect, even though SQL is the standard, there are like little differences in how they work and are implemented, so you need to make it aware of the engine itself. Like for example, in the case of Redshift, there's a certain thing you need to do with ambiguous column names, which other engines might not have that in the same way, and so on. And so normally, in order to make your structured data accessible as part of your generative AI application, you need to take care of all these things and build a solution for that. And this became a whole research area on its own. So there are like plenty of papers written about it, a lot of different suggestions what to do best. There are benchmarks by now trying to figure out who has the best solution for that. And it's a big pain for our customers. That's what we observed, because it's like really requires a lot of like ML experts to get it right. Since like this morning in Swami's keynote, we actually announced a new service called Amazon Bedrock Knowledge Bases for Structured Data Stores, which makes it damn simple to set up a natural language to SQL like knowledge base as part of the Bedrock platform. So we packaged all best practices and did a bunch of like additional things under the hood to give you really high accuracy and offer that now as a hosted service for you. Right? So it like gets you much faster access to the structured data. It's simple to set up. It provides like high accuracy, and it has a whole degree of customization options. And we also try to make sure all the time that this thing is secure and that things like SQL injection like don't work. Right? So there's safeguards built in. So with this, we actually have now a slightly different flow. So a request comes in. The generative AI application translated through the request is forwarded to the natural language SQL engine. It creates actually a query, which is sent to the database, which returns the result. And now you can include the result as part of your generative AI application. In addition, you can still use also traditional knowledge bases like documents and get like, let's say, top documents for your request as well. So you can include both, which then goes back together with the conversation history to the model and gives you the final answer. Right? Comes now in the, as part of the Bedrock platform. So this sounds like almost like magic. How does it work under the hood? Again, as said, there are a lot of things we do. Our magic weapon right now is like, so one of the key challenges is always if your request comes in, how do we ensure like that we select the right tables, the right columns, and other things? What we found is that often queries are repeating and that we can learn a lot from the query history. So one of our like tricks in quotation marks is that we actually analyze your query patterns you had in the past to figure out what columns are normally used most often, how they're joined together, and this is also part of the solution now to give you really high accuracy. I would say we do questions at the end. Okay. So just to give you an idea on how this whole process works, so if you go to Amazon Bedrock, you click on knowledge bases. Now there's a new option under create, which says like, okay, create a knowledge base with structured data. Right? So with that, you can select Amazon Redshift. You need to put in your credentials you have. Now you have two options here. One is like what type of Redshift instance you want to use, serverless or provisioned. You can pick what catalog you would like to use from the endpoint you connected from Redshift or the Glue catalog. And then, as we show here, there are a whole range of customization options we offer. For example, you can provide additional semantic annotations for the tables. So we take, if you know something more about a cryptic table name, please put it in there. It helps to create better queries. Right? The other thing is you can include or exclude specific table names or columns, and you can even give some query examples where you say like, okay, these are the typical use cases I expect, and we will make sure that we get those then right. In the moment you have all done that, you just create, and you create by that now you have a structured knowledge base. The next step is you need to give permissions so that this knowledge base is actually allowed to access the tables you selected in Redshift. So this is the next step, so that you make sure that it has the rights to select and query it. And that essentially are the main steps to go on running. The thing you just saw, the sync, is just like a forced mechanism to ingest all the metadata and start the query history analysis. It would happen also automatically, but you can also force it. And next thing, just select the model you want to use for the prompt generation, right? And then you're ready to go, and you can already test it. Important to notice here, for the generative sequence generation, we also use models and generative AI under the hood. What you select here before as the model is mainly the one which is used for the final prompt you send to the LLM before you get the answer back. Right? But otherwise, this is a complete hosted solution. And as you saw, this whole demo took roughly 2.5 minutes, was recorded in fairness, but it's very, very fast to set it up and get going. And there are many more features to come in the future. With that, I would like to hand it over to Mo from Nexthink.
Thank you, Tim. So I'm Mo Haidar. I'm coming all the way from Europe, Switzerland, to talk to you about Nexthink and our journey with our data platform and how it enabled us to build GenAI products efficiently. I'm an engineering leader / principal staff from the CTO office, and my job is simple. I take ideas and make them happen. Well, at least most of the times. So what does Nexthink do, and what's our mission? So we want to actually make employees' experience with technology seamless, efficient, and better. And we do that by providing a digital workplace platform, observability and automation platform that monitors and analyzes how employees use their devices and applications and technology in general. We also detect issues before they affect productivity and provides tools to fix them, remediate them, and automate them if they happen again in the future. And we offer insights to optimize IT systems. We have customers spanning multiple industries and regions, including some you probably notice. We also partner with major IT providers like Accenture, Wipro, etc., to provide our services to many customers. So how do we do all of this at Nexthink? So what's our secret sauce? Well, basically, it's the combination of data and AI. Clean, structured, and accessible data combined with the knowledge and intelligence generated by artificial intelligence. Today, I'm going to talk about the two parts. I'm going to talk about data and our data platform, and I'm going to explain how we use this data platform to create one of our GenAI products, Autopilot, that we've launched in Q4, and we're going to continue to launch it next year. So when we wanted to build our data platform, we had a couple of requirements in place. First, we wanted to support high growth for ingestion of new data. We knew that when we wanted to launch our platform 2 years ago, we needed to support 1 million endpoints sending data to our platform, and we knew we needed to scale to support 30 or 40 million endpoints in 1 or 2 years. We also needed to support high-frequency data lookups to support all of the different use cases and products that we wanted to build. And we wanted to support sub-second query speeds for all of the time series queries. And this is an ambitious set of requirements that we had to overtake. We also wanted to enable real-time use cases with minimum effort. We didn't want teams to reinvent the wheel every time they wanted to do a real-time use case. And last but not least, we wanted teams to move very fast when they need data, especially for AI applications. To give you an idea of our scale today, we have more than 20 million endpoints sending more than 5 million records per second to our data platform to be consumed, ingested, and stored in our databases. And at the point of the time of writing this presentation, we have more than 2.5 trillion rows in our time series database, taking more than 100 terabytes of data, and the different use cases and products that we have are querying this data more than 1 million times per minute. So to be able to tackle all of these requirements, we set a couple of principles in place. I'm going to highlight a couple of them. First, we wanted to leverage as much as possible managed services. We didn't want teams to spend their time operating and managing these services, especially at the scale. We wanted them to focus on building business logic and adding business value. We also wanted to make sure that the services we use basically scale to our requirements. Resilience is super important for us. In fact, it's one of our architectural characteristics. So we decided to choose asynchronous communication and event-driven architecture whenever it's possible to absorb all of this load and enable us to scale more. And lastly, we have more than 40, 50 teams working on these different use cases, and we wanted them to work in their own domains. So we decided to do microservices, which enabled us to scale organizationally and architecturally. So when we built this data platform, we leveraged two main services on AWS. Teams build their microservices and deploy them on EKS, Elastic Kubernetes Service provided by AWS, by Amazon. Teams will deploy their services, and EKS will run them and scale them automatically for the teams. And we use Amazon MSK managed streaming for Apache Kafka for communication, inter-service communication, and as our main streaming service. Let me walk you through briefly our data platform and how data moves in our platform until it's ingested and stored in our database. As I've mentioned, we have more than 20 million devices sending data every second to our backend. This data arrives into our platform by a microservice, and it's landed into a MSK topic. Then we've built our data layer to basically take this data, clean it, enrich it, transform it, and store it into an MSK topic so that it can be prepared and persisted into our different databases. And we use different databases for different use cases. We have a time series database for most time series use cases, and Amazon Aurora for relational data. One of our requirements was that we wanted teams to access this data very easy and simple. So we've invested a little bit of effort into providing a layer, a platform service where teams can actually use these platform services to access this data. Teams have to publish their query into MSK, and these services will basically query the data, prepare them, and stream them back to the teams within milliseconds. If you're interested to know more about all of this, I've written an article on AWS blog. Feel free to scan the QR code and read about it, or ask me questions later on about all of this after the session. I do want to highlight two main characteristics of this data platform that enabled us to move fast and do what we do. The first one is actually the structured data on stream. From the moment the data lands into our platform until it's stored into the database, it's structured using a schema-based protocol like protobuf. And we've enabled teams to access this data by deploying custom resources alongside their microservices. So team would define the topic they're interested in and the access level that they want to, and they will subscribe to this Kafka topic and get the data directly. And we've provided them with a set of libraries to decode, decrypt, and de-anonymize the data so that they can leverage them in their application without having to figure out how to do all of this. The second main characteristics that really allowed us to move very fast is our data model. So a data model is basically the different objects that we have, the user, the device, the events, and the relationship between them. And we've built a unified query language on top of that, which we call NQL, Nexthink Query Language. It's basically a piped language where you would describe what you want, the different objects and events, do the different joins that you want, and compute properties that you're interested in. We've actually made this query language available for our customers, so our customers can query all of the data whenever they want in near real time, and they get the result within seconds. And we've enabled our teams to use NQL to access the data and build features on top of them. And this allowed teams to move very quickly. They don't have to figure out where do I have the data, what's the type of the data, and the structure of the data. And as you've seen, we're really heavy on MSK. MSK is very critical to making this data platform work. So we have a lot of heavy usage on it. Traffic at any given time can oscillate between 1 to 3 gigabytes per second. We have more than 1 to 2 million messages coming into the system to be handled by MSK. So in production, we deploy 13 Graviton-based clusters. Every cluster contains 24 brokers with 3,000 to 4,000 topics and 16,000 partitions. And for people that are familiar with Kafka, that's actually a lot of Kafka topics and partitions to be handled by MSK. We also have data retention requirements. We require that topics have at least 12 to 24 hours retention, and teams can configure retention on topics to go more than a week. So we have seen in production that topics can grow to more than 5 terabytes in a week. To be able to handle all of this and operate smoothly, we've been spending the last year or two on some improvement that helped us, and I want to share a couple of them with you today. So first, we've moved to Graviton3 instances, and this helped us decrease cost and improve performance by 15%. We've also implemented rack awareness, and this helped us reduce network cost by enabling consumers to connect to the closest broker, ideally on the same availability zone. So in a perfect situation, you wouldn't have to pay cross-AZ cost. And this year, we've enabled tier storage on MSK. And tier storage is basically dividing the storage of your MSK clusters or brokers between cold storage and hot storage. So some of our topics, the data flowing through these topics need to be processed only once, and we keep them for reliability and disaster recovery. So we move this data into a cold storage, and only the fresh data stays in a hot storage. And this really allows us to decrease our cost on storage on MSK, and also in generally improves the performance and operations of MSK clusters. Finally, as Uday has mentioned, we try to stay up to date with the latest MSK versions. This basically, you get free performance gains, bugs are being fixed, and new features are being released. And we're looking forward to trying the new releases from MSK. And one important lesson that we've learned 2 or 3 years ago is that proactive monitoring is very important in MSK. So we've invested some time in building our dashboards on top of the different MSK metrics to be able to kind of monitor the service and proactively scale it whenever we need. So MSK is a good solution for us, and it kind of does most of the work for us. We just had a small team working on these improvements. And if you compare MSK to other providers, it provides good value for us. It's 3 times cheaper than any other provider there. And for our scale, that's millions of dollars. So now to talk about GenAI and how we built one of our GenAI products, which is called Autopilot, on top of this data platform. So let me first introduce Autopilot for Service Desk now, so that you know what I'm talking about. So one of the products that we offer at Nexthink is called, it used to be called Amplify, and it's being rebranded to being called Autopilot. So whenever you have a problem at work, let's say you cannot access SAP, you would basically open an IT ticket, and there's a service desk operator that will open your ticket and try to solve it for you. And he uses a product from Nexthink called Amplify, where they can access the different data that they have, data about your problem, your application, your network, etc., trying to diagnose what you have and fix it directly in the browser in the service desk system. And of course, Amplify offers some automation and remediation tools directly there. So this was actually a perfect opportunity for us to kind of implement GenAI solutions to make this user journey or the service desk operator journey much easier, faster, and reduce the time to recover to resolve this ticket. And that's what Amplify Autopilot for Service Desk does. And we do that by, for every ticket that's coming into the system, we basically, in real time, we help the operator do his work by minimizing the work he has to do. So Autopilot will basically summarize the issue and list all of the possible symptoms. So if you cannot access SAP, this could be because of your local network, because of a VPN, maybe the service globally is down. We have all of this data at Nexthink, and GenAI and foundational models, they're able to kind of to look at all of this data and give you the list of symptoms that would help you solve this problem quickly. So you save a lot of time then, and you don't have to kind of go and diagnose everything. We also provide in the product direct resolution plan to act on these symptoms and resolve them using remote actions, which is a Nexthink product, and workflow to kind of automate all of these things. And finally, we provide directly their list of insights and similar tickets in case the problem is not solved. These insights could help the kind of the service desk operator identify where the problem can and act on it. So let's look at how we do the generation of this issue and symptoms using our data platform that I described before. So when we have a ticket being flown, it's basically available in MSK. So the team basically builds a GenAI application. They would listen to these ticket creation events through MSK, and they will build a generative AI application use prompt engineering. And then they will leverage the data platform using NQL to get all of the relevant data about this problem, about the device, about the network, everything through NQL. And then they would pass it to the LLM to kind of list the different issues and symptoms there. One of the things that we've seen while developing and launching this product is that we're sending a lot of data to the LLM. And the more you send data to the foundational models, they might lose a little bit concentration, and the focus of your prompt might be affected. So to tackle this problem, basically, we would pre-process all of the queries. So for every query, we would run a small pipeline where we take the query, we pass it to the foundation model and tell it to summarize this data so that we can extract the most important data points. And then we pass these important data points to the query, to the prompt, and this prompt becomes now smaller, more concise, and the answer from these foundational models are usually more accurate. And you might be wondering, how do we know which NQLs to call for every ticket, especially that in IT problems are fragmented. There's a lot of categories. The problem could be with your device. It could be a global problem, or it could be a problem between the keyboard and chair. And the latter one we cannot really solve. So we started with a subset of use cases. We focused on a couple of use cases, and we predefined the NQL queries that we needed to launch for these cases. And we saw that this is working. Then we wanted the system to be a bit more flexible and to cover more use cases. So we've iterated and started to generate this NQL based on the ticket problem. So if your problem is with an application or web application, the system will generate a bunch of NQL queries that are related to this category. And we do that using a technology that we've created internally, which we call NL2NQL. It's a technology very similar to the one that Tim has described. So basically, NL2NQL, you give it a problem statement or a question. There's a workflow that will basically generate this query for you, and then you will have the output there. And we have to take into account when we're generating NQL to give it our complex data model and our schema, because foundational models have not been trained on NQL. They've been trained on SQL, but they don't know how to NQL and our query specifics. So how did we solve this problem? So we've implemented the RAG techniques that you're familiar with to solve this problem. And let me walk you through how we do it. First, we prepare the data. So we take the different data models we have, we embed them, and we store them in a vector store. And then we take the different labeled examples that we've generated and also embed them and give them in vector stores. These labeled examples will consist of expert-created data sets, so the different questions and the relevant answers, the relevant queries. Also synthetically generated data sets that we use a foundational model to generate. And also we take data from production after anonymizing it, feeding it back into the system so that we can improve and make our data sets bigger. So how does the NQL query generation workflow works? So when the question comes into the system, first we embed this question, we tokenize it, embed it, and we semantically search for the most relevant examples given a specific query. Then we take both of these, the question and the examples, and then we tokenize them, and then we semantically search for the most relevant tables and columns. For example, if your question is, give me all crashes on a device on a given date, this semantic search should return you the most relevant tables. In this case, it could be, I'm interested in the crashes table, I'm interested in the device table, and I'm interested to compute the number of crashes. You take all of this data, send it using a prompt to the foundational model, and then the foundational model will give you a query to be used in the system. So let's look how we build this and look at our architecture so far. So as I mentioned, ticket event is flowing through MSK. Then the team implemented the business logic that we described above via a microservice deployed on Kubernetes, on EKS, leveraging the data query services of the data platform. And of course, we have our embeddings layer where we take the different data sets that we have, we tokenize them, and we store them into our vector store, and we use Amazon OpenSearch service for this. We use Amazon Bedrock as our provider for foundational model and for our embeddings and endpoints. When the application generates the result, we basically put that back into MSK topic, and this will be ingested and stored in our database so that it's available for the front end to be loaded whenever it's needed. Now, as Tim has mentioned, that NL to SQL is not actually a simple problem. You have to put some effort to make it work, and that's not easier with our custom query language, especially that our language is proprietary. And these are some of the things that we've noticed after launching our solution. Our prompt was becoming big and dense. So in our prompt, we have the general instruction. You have the query-specific instructions from the constraints, the operations, the syntax. We also have the RAG examples embedded in the prompt and the schema details. So the prompt has become dense, and the denser the prompt becomes, the less accurate the response becomes. These prompts are also highly tuned for specific LLMs. If you wanted to change from one LLM to another one, you would see a degradation in the response. Even moving from one version to another, we've seen that our responses are less accurate. So we had to always tune them to specific LLMs. In RAG applications, generally a bad example has a considerable weight because in the prompt you're giving 2 or 3 or 4 examples, and if you have 1 or 2 of them as a bad example, then you're confusing the foundational model and the result will not be as you expected. And finally, these foundational models are not built or not trained on our business logic or specific jargon. So a blue screen for a foundation model could be the color blue, but for us it's a crash, especially if you're on Windows Vista. So this system that we've released basically worked for simple questions, and the more complex the questions are, the less accurate the queries happened. So after launching this solution, we wanted to iterate and improve the system. So prompting and RAG were good, but not good enough for what we wanted to do. So we've moved on to fine-tuning a model. So we've built a small model specialized in NQL generation based on code llama models using Amazon SageMaker. And this model now is smaller, better, more concise. It doesn't need instruction. It does know the syntax quite well. It has the schema there, and it has more than 50,000 examples of our data set in its memory. And the whole process of fine-tuning after you automate everything takes actually less than 2 hours. So the team has built this muscle of training or fine-tuning our model every 2 to 3 weeks. So either changing from one base model to another, or upgrading it, or even adding more data set to it. So every 2 to 3 weeks, we can release a better, more accurate, fine-tuned model. So let's plug this into our architecture. So we have our fine-tuning layer there in the AI layer using SageMaker and all of the tools around it. And then in the code, we simply needed to call this Amazon SageMaker endpoint versus calling the Amazon Bedrock foundational model. And we've seen great improvement in the quality of the queries that we generate. Now I want to actually highlight another part of Autopilot, which is the insights. So insights are basically these knowledge that we generate based on different techniques. It could be machine learning techniques from data patterns, anomaly detection, statistical analysis, and also using GenAI techniques. And to generate good insights, you need a lot of data. The more you have data, the better your insights are. So cross-customer data for us was super important. However, that wasn't simple for us because of our cellular architecture. So we have customers in different regions, and we needed to respect their data locality. So customers in Germany, they don't want to be connected to the US and vice versa. So we basically deploy our solution in standalone cells in different regions, and we route the traffic based on the customer to the different regions and cells. And this was a problem for us because that means that the data is now spread in multiple cells, standalone, and we don't have them in one place. To solve that problem, we basically centralized all of the data in a data lake. We basically take all of the data from a different cell, and the personal information never leaves the source. We move them securely to a centralized account that we call the data lake account. So now that we have all of the data in one place in S3, we basically generate these different insights, etc. For the sake of time, I cannot go into depth of how we do this. However, my colleague Nat have given a presentation in the AWS Summit. You can go online and watch his presentation where he goes into the detail of this, but I'll give you the gist of it. So after the data is in S3, we basically leverage AWS analytics services like Amazon Glue or Spark on EMR to take this data, process it, pre-process it, generate the different insights that we want to generate using different techniques, and then store these data into S3 buckets, replicate them into different cells, and then they're fed back into our data platform where they're stored in different databases and indexed in Amazon OpenSearch for retrieval later. And because we had all of the customer data in one place, and we have the insights and the knowledge localized, we also had a perfect opportunity to expose this data lake to our internal users. For less technical people, we basically leverage Amazon QuickSight dashboards so they can go and query the data and see everything. For more technical people like developers, they can use Amazon Athena to query the data in a more complex way. And of course, with AWS Take Formation, we've put in place the proper access right controls so that the different people see the proper data and we don't have a problem there. So feel free to kind of watch more in depth how we do this in this by scanning this QR code. So now I'll call back Uday onto stage to wrap this all up.
All right, awesome. Can you guys hear me? All right, thanks, Mo. So yeah, this brings us to the end of the session. Like I said, like the additional reading, that's all present on the slide. So feel free to take a picture. And yeah, and just wanted to thank you all for sticking around till 6:30 in the evening. Hopefully there's some good dinner for you guys somewhere in the Vegas Strip. So yeah, we'll, I don't know if you have time for questions. Only 5 minutes. I think we'll just answer questions off stage if you have.